Okay, let's see. Okay, as promised, I printed out these lecture notes in case you're like me and you have a hard time writing things down fast enough. This will allow you to just annotate. Alvis, they're on the website.
Very well.
Let's see. We're missing Jake and Tanner, who are at a meet. And then Jake Woosley, I think, should be here. Any questions about anything before we begin? All right, well, let's just continue. I mean, I hope this feels good because we're talking about, at least right now, a lot of things that you learned in modern physics, and they should sound familiar even though they didn't sink in, and we're sort of taking it to a deeper level, hopefully the understanding or reminding yourself at least about what all these words mean. Let me share the screen here. And well, actually, before I share the screen, let me just write down what we were doing. We were looking for solutions to the time-dependent Schrodinger equation, which I won't write down here. And out of desperation, we looked for separable solutions. And they were solutions that means product essentially forms. They separate into a product of a space factor and a time factor. So these special solutions, we might call them separable solutions, which are functions of x and t, are denoted by lowercase psi of x times lowercase phi of t. And we were able to figure out what phi of t is because it just had a perfectly well-defined differential equation that we could solve. And up to a normalization constant, it looked like e to the minus I e t over h bar where E was the separation constant that we introduced, right? We'll find out that, or I guess, I can't remember if we talked about how this is related to energy, but we will shortly. And then to find the, to find psi of x, we have to solve the time-independent Schrodinger equation. I call that the TISE because it's kind of a pain to write it all. And the time-independent Schrodinger equation says essentially the Hamiltonian operator acting on that function psi of x has to equal a constant times that same psi of x back again. And so the Hamiltonian is p squared over 2m plus v of x. So that looks like minus h bar squared over 2m d squared. Well, I guess it's an ordinary derivative now because things are only a function of x. Psi plus v of x times psi equals e times psi. That's a differential equation, and we've got to find solutions to the differential equation, and that's what we're about to start doing a lot of in chapter 2. And just to go back to what we ended on last time, we talked a little bit about this being a kind of eigenvalue equation. H psi equals E psi says, we're not looking for any old function. We're looking for functions where the Hamiltonian or total energy operator acting on it gives a multiple of the same function back. That's called an eigenfunction or eigenstate. And we said, as I'm showing in the slides here, we looked at these at the end of yesterday. Oops, that's not working well. Finicky pointer. Generally, if you have a generic eigenvalue equation or an equation for an eigenfunction for some operator, here we're talking about the Hamiltonian operator, but in general they look like this, they're probably not going to be normalizable for any old Q. And so the collection of Q for which these solutions will be normalizables, for which we'll actually have physical states, is called the spectrum. The allowed values of Q is the spectrum of that operator. So here we'd be talking about, if we're solving the time-dependent independent Schrodinger equation, the spectrum of E values, that's the eigenvalue here, the collection of E values for which the solution is normalizable is called the spectrum of the energy spectrum. And we can have cases where, as you know from the infinite square well, it can be a discrete, so you only have certain allowed energies, or in other cases it can be continuous, or as you know from the hydrogen atom, depending on how much you talked about it, it can be a combination. There can be a discrete part plus a continuous part. Okay, so we'll get back to, I'll just use that notation later on. I think that's where we ended up. So the next thing I want to talk about is, and I believe this is following the discussion that's in Griffiths, 3 useful properties of these separable solutions. Remember, these aren't the most general solutions. We just found some very specific solutions called the separable solutions out of desperation, and we're going to show their importance as we go on. First of all, they're what's called stationary states. Stationary means it doesn't change or it's sitting still, and what doesn't change in a stationary state is the probability density. And so in this case, when we say stationary states, that means that all those probability density functions are independent of time. If you're in one of these separable states, they're all independent of time. Now, we don't know how to, again, haven't shown, and we won't get till chapter 3 to figure out how to draw a picture or get the functional form of rho as a function of px or e or anything like that. But we do know how to get rho of x. So let's just check it for rho of x. Let's get back here to the screen. Rho of x is psi star psi. This is the full psi. You got to keep in mind the difference between capital psi, which has these little serifs on it, and the lowercase psi that doesn't. Psi has this form. lowercase psi of x times e to the minus I e t over h bar, where e is one of those allowed energies, right? I guess I should have written this farther over. Okay, so I'm going to write out psi first, and then we'll put a psi star next to it. Psi of x times e to the minus I e t over h bar. And let's put a psi star next to it. That's going to be psi star of x times e to the plus I e t over h bar. And these are just ordinary functions of x and t, so we can commute this through over here, and these two things multiply together to give 1. And so what we're left with is just a function of x, but it's not a function of t. It has no t dependence, and that means that rho of x is going to be independent of time. The same, we claim, is true for all other probability density functions, but that shows it's time independent. It's also true that the expectation value of for a time independent operator, an operator that doesn't depend explicitly on time, and all of the operators we've talked about so far don't depend on time. So if I take the expectation value of some operator q, which is a function of x and px, right? We're told the formula for that is you integrate, and what you do is sandwich that operator in between a psi star, that's the full psi, the capital one. So that would be lowercase psi star of x times e to the plus I e t over h bar. Then we put our q operator here, which is a function of the x operator and the p operator. You could write that as the px operator if you wanted. And then over here, I've got a psi of x times e to the minus I e t over h bar. This is all in the notes there. And then we're supposed to integrate with respect to x. Blah, what a mess. But it's not such a mess. The important thing is that this is just multiplication by x, and this has derivatives in it. So this thing might involve multiplying by x's and taking various, orders of derivatives of what comes to the right. With respect to derivatives with respect to x and multiplying by x, this is just a constant. So I can pull this doesn't have any x dependence in it. So it may as well be the number 3 or something like that, right? So I can pull it over here, and it can cancel this one out again. Those two can still cancel because this is an operator that only really cares about the x's that follow. It doesn't care about the t's. And so what you can see, what's left doesn't depend on t. The integrand doesn't depend on t. So this whole thing is time independent. I mean, we could have gone, of course, if all the rows are time dependent, then you should believe the expectation values are time dependent too. But we only proved that one of the rows was time independent. But here's another indication that, wow, whatever rho is as a function of q, if it's time independent, we at least expect the expectation value to be time independent. We also expect the spread or the uncertainty to be time independent, and any other thing you can compute from it too. So those are just a couple of different illustrations there. So we have 3 different names that I say in the notes, if you're following along here, for these kinds of separable solutions. We can call them separable solutions, things of this form, the product form, function of x times the function of t. We call them energy eigenfunctions because the time-independent Schrodinger equation for this is the energy eigenfunction solution, and multiplying by that function of t doesn't change the fact that it's an energy eigenfunction. And finally, we call them stationary states because the probability densities are all time independent. So if it's in one of these states, the claim is if you measure something, doesn't matter when you measure it, the outcome probabilities are going to be time independent. So it doesn't matter when you measure it, you'll have the same relative probabilities. Okay, let's go back to here, share screen. They're states of definite energy. Well, one way to show that they're states of definite energy is, what that means is, if I have a state that has a definite energy, right? If I had a state of definite position, right? If I said, oh, the position of this particle is definitely x0, there's no uncertainty about it. What that would mean is that rho as a function of x would be kind of a Dirac delta function. In other words, the expectation value would have a certain value, and more importantly, the spread would be 0. The uncertainty should be 0. So if these are states of definite energy, when I'm imagining rho as a function of E, it should just be peaked at a particular value, and the uncertainty, or the standard deviation, as Griffiths writes it, should be 0. Let's check that. The expectation value of H, so we're going to eventually calculate sigma of H, and we want to show that that's 0. Sigma of H is going to be, well, let's calculate the square of sigma of H. That's the expectation value of energy squared minus the expectation value of the energy operator squared. And if we took the square root, that would be, so we're going along the way to there, right? Let's calculate the expectation value of energy. Same way we did before. That's the integral of psi star, which is a function of x, times e to the I et over h bar, times the total energy operator sitting in here. I'm just going to abbreviate that with h. So I'm sandwiching h in between a psi star and a psi. Psi e to the minus et over h bar. And you integrate with respect to x. That's our formula for calculating an expectation value. Now, h, like any dynamical operator, only depends on x and derivatives of x, right? Because it's a function of x hat and p hat. So it doesn't really care about this thing, but we already know that, what does this mean? It's a solution to h psi equals e times psi. So I can just replace that h psi with an e psi in there, because by definition, psi is a solution to that equation. And therefore, when that happens, I can cancel these things out. The e is a constant. It can come out in front of this x integral, right? We're integrating from minus infinity to infinity. So that's going to be e times the integral from minus infinity to infinity of psi star psi dx. And if we want our full capital psi to be normalized, these psi's have to be normalized as well. So we're always going to normalize the lowercase psi as well in this case. So that's going to be 1. And so this is equal to e. Almost exactly the same argument, right? What's the expectation value of h squared? Well, I need the square of the h operator in there. Again, same thing happens. H times psi gives an e times psi, and then the second h times psi gives e times psi back again. And so I pull out an e squared out in front, right? This gives an e squared. The e squared comes out in front. What's left is a 1. And so when I calculate this, this is e squared minus e squared, which is 0, which means the expectation value is a certain value of e, and the spread is 0, which means that's a definite value of energy. In other words, that's justifying that the probability density function looks like this as a function of E. Okay, so it's a state of definite energy corresponding to that constant E. Okay, that means if I measure energy and I'm in one of those states, there's only one energy I'm going to get. Third, page 21, the separable solutions, which right now just seem like, you know, okay, it's sort of somewhat interesting that we can find these separable solutions, but so what? They're not all the solutions. Here's the big deal. The separable, the time-dependent Schrodinger equation, and I'm sorry, I should keep remembering to unshare the screen for Alvis. The time-dependent Schrodinger equation, easy to check, is linear. Linear means a linear combination of any two solutions is a solution. That means a linear combination of any number of solutions is a solution. And so if we can find an infinite number of solutions, for example, we'll find that there are always an infinite number of solutions. And the question is, and that means there's an infinite number of allowed different E values, which are solutions. Maybe I should write that down. H psi equals E psi as solutions for an infinite number of E's. Now, that infinite number could be discrete, as you're familiar with from the square well, right? There's an infinite number of energy that are allowed, or it could be continuous. We'll see several examples of those this term. If the spectrum is discrete, we have an infinite number of different solutions, right? So let's suppose the spectrum we might write as En, if we're using the notation from the infinite square well, right? N equals 1, we usually call the ground state, N equals 2, the first excited state, and they keep going up, right? So we'll say N equals 1 to infinity. In other words, I'm saying here's a collection, a set, and there's one of them for each N. Starting, there's an E1 in there, there's an E2, there's an E3, all the way up towards infinity, right? That's a discrete infinite spectrum. That means I have, for each one of those E's, I have a linearly independent solution. And since I'm indexing these by N, we usually index those psi's by N. They're all linearly independent. And since the time-dependent Schrodinger equation is linear, well, I guess we could say this is the solution to the time-independent Schrodinger equation. Here's the corresponding solution to the full time-dependent Schrodinger equation, minus I ET over H bar. So there's, and the E, that we're using En here. So that's a particular solution that happens to be separable. There are an infinite number of them, and therefore, this function, psi of x and t, which is an infinite linear combination of these, the sum from 1 to infinity, with different coefficients. People usually call these coefficients Cn, but this is supposed to be for n equals 1. There's some number sitting here. For n equals 2, there's some number sitting here. Could be complex. Times each of these, psi n of x, e to the minus I En t over h bar, is also a solution. TDSE solution. Okay, that's because the time-dependent Schrodinger is linear. If each one of these is a solution, any linear combination is a solution. And it turns out this is the most general solution. So if we could just figure out what those coefficients are, and those coefficients depend on what state, at time t equals 0, maybe we say the shape of psi of x at time t equals 0 looks like a particular shape. That particular shape is going to determine these CNs. And then this formula, even though it may not be your best friend because it's an infinite series of functions, is going to tell us how it changes from there on out. And we'll see examples of that. Okay, so that's the discrete spectrum case. If it has a continuous spectrum, generally, when things are discrete and you want to add them up, you use a sum. When they're continuous and you want to add them up, you use an integral, right? Integral sort of adds up little bits that become continuous, like adding up the area under the curve. So in that case, the most general solution, psi of x and t, can be written this way. We integrate over all the allowed values of E. And in this case, they're a continuum, so we're going to integrate over some range of E. You're integrating over the range of E, which forms all the normalizable solutions. Maybe I'm just going to imagine, maybe that's integrating from E equals 0 to infinity. Okay, we put an arbitrary coefficient in there, which is different for every E. Right, just like for each En, we had a different possibly a different coefficient here. For each e, and now e is a continuous variable, we have a different coefficient out in front, multiplying the separable solution corresponding to it, and we integrate with respect to e. Okay, so these are like two sides of the same coin. Discrete case, we have an infinite sum. Continuous case, we have a continuous sum, which is an integral over the range of allowed e's. You know, it doesn't have to be e equals 0 to infinity. It's whatever range of e's corresponds to the collection of eigenvalues. Okay, so those are three big, go back to sharing the screen here. Three big things. They're stationary states. They're states that have definite energy, so the probabilities don't change with time. They correspond to one and only one energy. So if you measure energy, you're only going to get one value. And the general TDSE solution is an infinite linear combination of those separable solutions. So even though we got them out of desperation, we'll find, doesn't matter what you want this to look like at time t equals 0. You give me the function at time t equals 0, in principle, we should be able to solve for the CNs. And you probably did that in modern physics, but probably have forgotten about it. So let's do the case that you're most familiar with from modern physics, the infinite square well. When I say what energy? No, not that it's quantized, but when I say each one of these, so when we're saying, let me flip back there, you're talking about their states of definite energy. We're talking about these separable solutions, right? Not the most general solution. And what that means is, if it's a state of definite energy, then rho as a function of energy would be non-zero only at one value. And that means if you measure energy, that you're only going to get that one value. The probability is 0 everywhere except at that one value. So, for example, we're about to talk about the solution to the infinite square well. There you would say, oh, okay, I could be in the second excited state. That would correspond to n equals 3, right? N equals 1 is the ground in the usual way we number it. N equals 2, first excited state. N equals 3 is the second excited state. And you kind of know, if you have your square well, we'll talk about this. The second excited state for psi, the lowercase psi 3 kind of, does something like that. It's got like 3 bumps in it, right? 2 upper bumps and 1 down bump or something like that. So, and then it goes to 0 outside of there, where the potential goes to infinity. What that means, and here we have E3 over here. What that means is if you're in this state and you somehow come up with an experiment that measures the total energy, the claim is you should only get this one value. If you set up 1,000 iterations of this state, somehow, let's not worry too much about that now, but you're able to set up 1,000 iterations of that state, and you measure the energy on all of them, you'll always get the same number for the total energy. Okay, back to here. So the infinite square well, we're just to introduce the notation, we're going to imagine that something is pinned in by a potential energy that goes to infinity for x less than 0. So the potential is infinite over here. It's infinite for x greater than a, over in this region. And then it's 0 in between x equals 0 and a. So that's what the potential looks like. And let's start solving for cases. In the first case, the easiest case to do, although it's a little bit confusing just because we're not used to solving things in cases where functions go to infinity, but let's solve for what psi has to be in this region out here, either x less than 0 or x greater than a. That's where the potential is infinite. Or you can think of it as really, really, really large compared to, the 0 value it has in the middle. If I look at the time-independent Schrodinger equation, so we're trying to solve for that lowercase psi, has to satisfy the time-independent Schrodinger equation. In this differential equation, if we're going to have a finite E over here, V is going to be infinitely large in this region over here, x less than 0. And therefore, the only way to make this be a finite number times that finite psi again is to make psi equals 0 in that region. So, you know, one way to convince yourself of this is you might think, well, what if V is just really big over here? You know, it's 10,000 joules over here, and then it goes down to 0 over there. You could convince yourself that the relative amplitude of psi in this region is really small compared to what it's going to be in this region. But in this case, that's an argument that psi has to be 0 everywhere in the region where V goes to infinity. So it's not much of an argument, but psi is 0 there and psi is 0 over there. Okay, that's the first case. Oops, wrong way. Second case. If we're in the middle of the potential well, there we're assuming the potential energy is 0. And so we can just throw away that V term in the time-independent Schrodinger equation. And that's not such a bad differential equation to solve. If you talked about one differential equation that's second order in your ODEs class, this might have been it because it comes up so often and you can solve it analytically. I'm going to take these constants, the minus h bar squared over 2m, and flip them onto the other side. When you do that, you get a 2me over h bar squared with a minus sign in front of it. And we're going to make the definition just a shorthand definition so we don't have so many constants sitting around. Let's define k to be root 2me over h bar. Well, you can see I have a 2me here over h bar squared. So this is going to be looking like minus k squared. So in terms of this made up variable k, it's just shorthand. This differential equation becomes d squared psi dx squared equals minus k squared psi. And that's your good old friend, the harmonic oscillator differential equation, whose solution is cosines and sines as functions of x. It's a second order ODE, right? So I expect two linearly independent solutions, and that's what we're seeing there. One is cosine of kx, one is sine of kx, and you just know when you take two derivatives of cosine, you get back to cosine, but you get a minus sign, and you pull out two factors of k. So it's going to end up giving minus k squared times the original function back again. Same thing for the sine in there. Okay, so that solution is pretty easy. The general solution in the middle is cosines and sines. Now the only thing that remains is to connect them up. We have to connect together the solutions at the boundaries between the regions. And we've got to talk about some boundary conditions, and we haven't yet in this course, so we want to talk about them somewhat carefully. So what I'm saying down here is the whole reason, you know, you might think we're talking about different regions. We have 3 different regions for this potential. The reason we're talking about 3 different regions is because V of x changes really drastically as you go from one region to the other. You can just think of it as one complete V of x, but something kind of drastic is happening there. And what exactly has to be true of psi at a boundary depends exactly on how drastically the potential changes there. So let's consider what has to be true of psi as you cross that boundary in this problem and in some other problems. In other words, as you're going from one region of V to another, let me unshare the screen now. The question is, well, in general, how crazy of a function can psi be? Can lowercase psi be discontinuous? Can psi prime, the derivative of psi with respect to x, be discontinuous? If psi prime is discontinuous, that means psi has a kink in it, right? I'm just going to put disk and then parentheses. That means we have a kink in the function. If it's not clear to you, you can, if it's discontinuous, if the derivative is discontinuous, that means the derivative jumps at some point. So it has a kink in the function. Well, the answer depends on how crazy you're going to let V of x be. right? So if we're crossing a boundary, it depends on how crazy the transition of v of x is in that region. So we're only going to consider certain kinds of potentials, and that's going to put limits on how crazy psi can change as we go across a boundary. Okay, so the answer to this question depends on what kinds of functions v of x we consider. And so we're going to limit ourselves to basically 4 varieties. And then we're going to see what has to be true of psi for all 4 of those varieties. Can it have kinks in it? Can it actually be discontinuous? Let's see. Okay, so our cases are going to be the easiest case. V of x is continuous. You know, this would be the case like the harmonic oscillator potential. It's just proportional to x squared. There's no discontinuities anywhere. It's not crazy at all. It's continuous at every point. Okay, so that would be it. You know, I'm saying v of x could have kinks in it, but at least it doesn't have any jumps. So my v of x as a function of x, you know, might have some kinks in it, and it's doing its own thing, but there's no breaks in the function. Second case, v of x has finite discontinuities. This would be like the case of the finite square well, right? That you looked at, I think, in modern physics, where it's down here and then it jumps up to a finite level and then keeps up there forevermore. Okay, so our v of x there might be down here and then suddenly jump up a little bit, right? But it doesn't jump up an infinite amount like we're talking about here in this infinite square well. It's only jumping up a finite amount. Okay, next case, v of x has infinite discontinuities. Okay, and that's the case of a hard wall like we're considering in this problem. I don't know how to draw that. I probably should avoid drawing these, but it's like your potential is doing what it does, and then all of a sudden it shoots up to infinity forevermore, or maybe for a while, and then shoots back down. But in our case, it shoots up to infinity, and then it just stays at infinity over there. And the fourth case, which, you know, probably isn't highly motivated now, but it's going to be able to help us illustrate some interesting kinds of spectra that otherwise are hard to get at, is if we allow v of x to have delta functions, Dirac delta functions. The particular case you're going to see later this chapter is that v of x as a function of x, we want to imagine we've got something like a square well, but we're going to make it really, 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 really thin, but also really, really, really deep. And so the potential energy function is going to look like the negative of a Dirac delta function. It's a really thin but really deep well. And, you know, we'll just see that it's actually pretty easy to solve the time-dependent Schrodinger equation. It's not like this is modeling a problem we're definitely going to encounter on a daily basis. Okay, so you just got to keep in mind those 4 cases. I want to keep erasing over here just because the camera is aimed at this part for Alvis. The first thing to realize is that in all these cases, in all these 4 cases, psi is continuous. Okay, you probably remember that something from modern physics about you can always count on the fact that psi is continuous. What's a justification for that? Well, let's write down the time-independent Schrodinger equation. So here's the justification. Let me solve for the second derivative that exists in the time-independent Schrodinger equation. So the second derivative of psi is equal to 2m over h bar squared times v of x minus e times psi of x.
All right, I'm not certain what it is, but the camera suddenly went fuzzy.
Maybe I kicked the cord. But, oh, it's probably, I bet what it is it's on autofocus. And I should get the
There it
app
is.
installed so that it will, is it focused now, Albus?
It's back to normal.
Okay, it probably focused on my back or something like that and then stayed that way for a moment.
Oh dear.
They ought to have something installed so you can just turn off autofocus because unless people are moving the camera around all period, you don't really need it to autofocus. Okay, so in this case, let's suppose that, well, I guess one thing I should have mentioned is that I should have said this before, but not in our list, v of x cannot have derivatives of delta functions. Okay, well, I've got to say what a derivative of a delta function is. Well, we know from our, let's see, I guess Alvis really can't see over there. If I have a delta function, right, we think of a delta function as something like that goes up very rapidly, and I'm going to draw it as if it's just a very narrow Gaussian function, right? That. So it's something that goes up and then it comes down to the same value. That's delta as a function of x. What would the derivative of a Dirac delta function look like as a function of x? What shape would it have? The point is that it's not like the delta function, but let's see. Its slope of this function is 0, 0, 0, 0. And then for a very short period, it's extreme positive, right? Almost infinity. And then very soon after that, it goes extreme negative, and then it goes to 0. So here's a function that goes extreme positive, and then extreme negative, and then back to 0. You could consider a potential like that, but I'm just saying we're not going to have any use for it, so we're going to throw it out, right? We're not going to allow v of x. We're just not going to consider any v of x's that have derivatives of delta functions. If that were the case, psi might be discontinuous, but in this case, that's not going to be the case. So v of x can't have derivatives of delta functions. So let's suppose psi is discontinuous. Let's suppose psi is discontinuous. If psi is discontinuous, right? If psi, I want to show that psi has to be continuous. If psi is discontinuous, okay, let's draw a little picture of a discontinuous function. If psi as a function of x suddenly jumps up to some other value like that, right? Then psi prime, what is psi prime going to look like? Well, let's see, psi prime, it's sort of, at least in my example I've drawn here, psi prime was 0, 0, 0. And then psi prime goes up towards infinity, right? It really is infinitely steep if this is really jumping up discontinuously, right? So it goes up to infinity, and then it goes back to 0 again, or something finite. So that means if psi is discontinuous, psi has delta functions. And then psi double prime has derivatives of delta functions. Okay. This side has derivatives of delta functions. Now we assumed that this is not, at least for the cases we're going to consider, this is not going to have any derivatives of delta functions. And therefore, in this case, since psi just has a discontinuity there, v of x would have to have a derivative of a delta function if this side is a derivative of a delta function. If we're just considering that psi is discontinuous here, then v of x would have to have a derivative of a delta function. But we're assuming v of x doesn't have a derivative of a delta function, and therefore psi can't have any discontinuities. Okay, so our first assumption, or our starting assumption, which comes from looking at the time independent Schrodinger equation, is that psi is continuous. Oh, and I shouldn't have erased that. I want to still look at that version of the time independent Schrodinger equation. Second derivative of psi with respect to x is some constants times v of x minus e times psi. Okay, now let's go through our 4 cases and see what has to be true of psi double prime and psi prime. Okay, our 4 cases are: if v is continuous, if v is continuous, e is just a number. So this thing is continuous. We decided that psi is going to be continuous, at least in the restricted cases we're going to look at. So the whole right-hand side is continuous. And that means that the second derivative of psi is continuous. And if the second derivative of psi is continuous, you can integrate that function. You'll find that so is psi prime. Okay, so if v is continuous, we're going to find out not only is psi continuous, but psi prime is also continuous. Okay, let me try to go through these a little bit faster, and we can talk about the technical details maybe outside of class. If v has finite discontinuities, if v has finite discontinuities, psi is continuous. That means the right-hand side would have finite discontinuities because e is just a number, right? So this has a finite discontinuity. The whole right-hand side has a finite discontinuities. That means psi double prime has finite discontinuities. If psi double prime has a finite discontinuity, when you integrate that, what is that going to tell you? Is psi prime going to be discontinuous, or will psi prime be continuous? In other words, if I have a function that looks like this, right, as a function of x, and I start integrating to position x, right, and I say there's a certain area under the curve. As I increase x, does it ever have a discontinuous jump in the value? No. Actually, it's going to be going up at a certain rate as I integrate to larger and larger x's. And then after that time, it's going to switch to a different rate. So it will have a kink in it, but it will still be continuous. This all requires, probably too much thought for this little time. Psi prime is continuous, and we already decided psi is continuous. So that's a case where we can rely on both psi and psi prime being continuous. Not so good for the last 2 cases. If v has an infinite discontinuity, well, let's think about what happens if I take this higher level and I bring it up and up and up, higher and higher. So I'm making that discontinuity go to infinity. What's going to happen to the picture I was making here? How should I change what happens before or after there if I'm raising this second level higher and higher? How is my integral function going to change? Yeah, the slope of that is going to get bigger and bigger and bigger as I move this up and up and up. And as I move it infinitely far up, it's going to go up infinitely fast there. And that means it's going to have a discontinuity, right? If something instantaneously goes up, it's discontinuous, okay? I know this is just a lot of details here, but this is an important thing to map out. That means that, of course, psi double prime has an infinite discontinuity. What we're going to be concerned with is that psi prime is discontinuous. Okay, that's what we're showing. As this discrepancy between the 2 levels there gets higher and higher, the slope at this, jump point of the integral of that function gets more and more vertical, okay? And something similar happens if V has a delta functions in it. In that case, well, let's think about what happens. If V has a delta function and this is continuous, the whole right-hand side has a delta functions. So that means that psi double prime has a delta. If psi double prime has a delta function in it, what does that mean about psi prime, the integral of psi double prime? So here's psi double prime. It's got a delta function in it. Let's imagine there's an area 1 under the curve or some finite area. When I integrate this function, it's going to be going along nicely, right? Maybe there was some area over here. So I've already gotten some area. And then what happens as I cross this point? It jumps up, right? Because all of a sudden I get a finite amount of area that I've gotten in my integral in that short amount. So it has a discontinuity, okay? So that means psi prime is discontinuous. Okay, it seems like an amazing mess, but now we're just going to summarize this in one statement of what we found out there. Hopefully I've got this written in here. Yeah. Somewhere here. Okay, so here's the summary. If you look at all these cases, this is what we found for the kinds of potentials we're going to limit ourselves to. When you're applying boundary conditions at a place where maybe V does something a little bit crazy, in all cases, we found that psi is always continuous, but psi prime may or may not be continuous. And the case that it wasn't continuous were the cases where it went to infinity somewhere, okay? Either we have a place where it went from a finite value up to infinity forevermore, or maybe there was a Dirac delta function, so it went to infinity. Those were the two cases where psi prime is not going to be continuous. Okay, so sometimes we'll have two boundary conditions, sometimes we'll just have one boundary condition, and we'll just have to keep that in mind. The important thing for us is, for me to check the time, we're going to go back and apply our boundary conditions for the infinite square well here. Okay, so what I'm going to do is apply the fact that at 0, at x equals 0, the function itself has to be continuous. Maybe I should draw a cartoon here. I know you guys thought through this before, but it's worthwhile thinking through it again. So here, our psi looks like a sine of kx plus b cosine of kx. And out in this region, it's 0. It's 0 here, right? So this function's got to match up with 0 in a certain way, right? And our potential, I'm sort of drawing the potential and the wave function on the same thing, or the time-independent Schrodinger equation, the same thing. Potential is infinite over here. So our potential goes from a finite value to infinity. And that's one of the cases where I don't know that psi prime might have discontinuities in it, right? But psi itself should always be continuous for the kinds of potentials we're considering here. So all I can really count on is the fact that, well, if it's 0 over here, when I evaluate this at x equals 0, which is where we are on the x-axis, here we are at x equals a over there. When I plug in x equals 0, it better be 0. Okay, so psi of 0 equals 0. What does that mean in terms of the selection of consequences we have down here? This is when you're supposed to vote with your voting things. If you don't have your voting sheet, just hold up your fingers, 1, 2, 3, 4, 5. Waiting to see. We have a majority of B's in this case. Anybody want to explain the argument for B being 0 here? Riley? Yeah. Right. So when I substitute in x equals 0, it better be 0 there in order to be continuous, right? That's this statement. And so tell me how to simplify here. What's the next step to show that b is 0? Yes, sine of 0 is 0, right? The sine function goes to 0. So this is 0 right here. And therefore, this whole term goes to 0. Cosine of 0 is 1. And therefore, that equation reduces down to b equals 0. So I can throw away the cosine part, as you're very familiar with, right? Okay, any questions on that one? You got to actually write it down to figure it out, or maybe you could do it in your head. Okay, let's do the same thing over here. Psi has got to be continuous over here, and I know the function is equal to 0 outside of the square well. So when I plug in, so we've already gotten rid of this part. Let's just forget about it. Let's erase it. We've simplified our psi. Hey, now we've done one of the boundary conditions. Now I'm going to say psi has to be continuous across here. It's 0 over there, and it's this function there. What does that tell me of the selections we have here? This one requires, a little bit more thought, but you've done the thinking once before, presumably. Okay, the C's have it. Everybody's voting C. I agree. Okay, so in this case, what I'm going to say is when I plug in x equals a, this function has to have headed down to 0 in order to be continuous. So that's the equation a sine ka equals 0. Product of two things equals 0. That means either this one's 0 or this one's 0. Now, if a is 0, we're in trouble because we don't have a normalizable wave function, right? That means our lowercase psi would be 0. That means our capital psi is 0. It's not normalizable. We're not interested in it. So this one can't be 0, and therefore this one has to be 0. The only way for the sine of Ka to be 0 is for Ka to be a multiple of pi, because that's when sine goes to 0, right? 0 pi, it's at 0. It's back at 0 at 1 pi. It's back at 0 at 2 pi, and so on forevermore, right? Same thing for the negative values. So that means that Ka has to be equal to an integer multiple of pi, where n could be any integer, right? 0, plus or minus 1, plus or minus 2, and so on. And therefore, what I'm finding is k is n pi over a. I don't have the n's matching up here, but there's some restrictions that we can do in simplifications. First of all, I can't allow n equals 0. Why? What's the problem? So suppose I say, okay, I'm finding out something about k, and I'm saying k is going to be n pi over a. So there's my function that we found out. What's the problem if n equals 0 in terms of a physically relevant function we're going to have here?
I'm thinking that if n equaled 0, the energy would also be 0. So there would be nothing at all, let alone a wave function for it to be described by.
Well, there's nothing in principle wrong with the energy being 0, but if I plug in n equals 0 here, how could I simplify this formula? It would just be 0 because the sine of 0 is 0, and I have the same problem I had before with setting a equal to 0, right? Then this whole solution would be 0, right? We'd have a wave function that, or a lowercase psi that's 0, 0, 0. When I multiply by the time part and get the separable solution, it would just be 0. And that's not normalizable. So we can't accept n equals 0 because it wouldn't make it normalizable. And similarly, for all the negative numbers, we know that, for example, consider n equals -2. Then I would have a function that looks like the sine of -2 pi x over a. We all know that sine is an odd function, and I could write that as minus the sine of 2 pi x over a, which is, what I've got left here, except for the minus sign, is the one that corresponds to +2. So every negative one can sort of be turned into the corresponding positive one. So they're duplicates of each other, right? I don't get any new genuine solutions from the negative one, because the negative one is just a multiple of the positive one. They're not linearly independent solutions. So we don't really need to keep both of them. It would just be excessive confusion. And that's why, in this case, the n's are restricted to the positive integer. You guys probably didn't think about that, but was the argument you made way back when. Okay, so that means we found our solutions. We said, remember, we can't require that psi prime is 0 at the two boundaries, but we have required that psi is 0 at the two boundaries. And we found that the general solution for psi at all x's, it's either sine of n pi x over a if x is between 0 and a, or it's 0 in the other cases, x is less than 0 or x is greater than a. And there's an arbitrary constant that we can put out there. We haven't normalized it yet, and I won't go through the details, but you can integrate this function, the magnitude squared of this function, from -infinity to infinity. If you normalize lowercase psi, you're going to normalize uppercase psi, because I don't know if it's worth writing this, but psi of x, if I do psi star psi, I get psi of x e to the I et over h bar. Is that a sign that we're out of time? No, not quite. Times psi of x e to the minus et over h bar. When I do that, right, and I integrate from -infinity to infinity with respect to x, these parts cancel out. And so if I want this integral to be 1, that's the same as having to normalize the lowercase psi. And I want to normalize it. What does Griffiths find or show that this equals? Just by doing an integral of sine squared is what you have to do, right? You probably remember it as √2 over L or √2 over A. Here I'm following Griffiths and saying the width of our well is A. So those are our solutions. And notice we found an infinite number of them. N equals 1, 2, 3, and so on. There's an infinite number of them. And where we're going to go starting on Monday is start combining them. I was hoping we were going to get to a worksheet today. So this is saying the separable solution looks like this. There are an infinite number of them, one for each positive n. Psi n of x is √2 over a times the sine of n pi x over a, or it's 0 if it's outside the well, right? And that means, I'm sorry, the separable solution, I was going to say, the separable solution is my capital psi, which is separable. This times e to the minus I ent over h bar, and en is related to kn by our formula we gave before. We said our k was shorthand for √2 me over h bar, and that means that e is equal to h bar squared k squared over 2m, or p squared over 2m, if you like. So if you plug in the allowed k's, you'll get the allowed e's. Okay, and that tells me that en is n squared pi squared h bar squared over 2m a squared if you plug in the allowed n. So these are the separable solutions. We might call that the nth separable solution. And the most general solution is going to be an infinite linear combination of those with arbitrary cn's out in front of each term. And our goal now is to say, well, if somebody wants to set up the system at time t equals 0 so it has a certain shape, what should the CNs be? We'll save that for Monday. Any questions? I was going to collect your homework today on numbers 1 through 8, and I almost forgot.
How do I turn in that homework?
You can just take photos of it or scan it, whatever. If you have a scanner at home, that would be great. But usually people just take photos and attach them to an email, and I'll print them out and grade them and just scan them and send them back to you.
Very well.
And I think I haven't updated the website, but I hope to before the end of today, showing that our homework, the rest of the chapter 1 homework will be due on Wednesday. Rather than having the next 4 be due Wednesday, we'll just have all the rest of it be due on Wednesday of next week. Okay. That's okay. I'm sure we don't have a stapler in here because everything's been cleaned out, although Dr. Neiser may have had a stapler at one point. We'll have to get one in here. I'm just going to dog ear it till I can get it to a place where we can staple it. Maybe I can get a stapler to put in here. Thank you. Alvis, do you have any questions before we sign off?
Not at all.
No. Okay. I'm going to end the session then.
Very well. Have a good day.
Have a good weekend.